In this module, you'll see how CUDA actually drives H100 and H200 GPUs. We'll connect kernels, threads, blocks, and the CUDA memory hierarchy to the Python code you already write. So framework magic turns into a clear mental model of what the hardware is doing. Start by contrasting CPUs and GPUs. A CPU is like a few extremely fast sports cars, great at complex routes, branching logic, system tasks, and low latency responses. A GPU is more like a huge fleet of trucks on wide highways. Each truck is simpler, but there are many moving in lockstep. That massive parallelism makes GPUs ideal for workloads like deep learning, where you repeat the same math across huge tensors. To understand how GPUs run deep learning workloads, think in three spatial levels. At the top, a grid represents one kernel launch, all the work for an operation like a matrix multiply. That grid is split into blocks. Each block is a team of threads that can synchronize and share fast local memory, which is ideal for operating on tiles of a matrix. Inside a block, the hardware actually executes in warps, groups of 32 threads that step through instructions together. Efficient CUDA code aligns its work with this grid block warp hierarchy. Take a simple example, adding two tensors element-wise. The hardware treats this as thousands of tiny, identical jobs. Each output element key is computed by an independent thread that reads A and B, performs one addition, and writes the result. You don't write an explicit loop. The accelerator launches a grid of threads, and they all run in parallel. This one thread per element pattern is the backbone of high-throughput tensor math on GPUs, TPUs, and NPUs. CUDA memory is organized like a pyramid because distance from the compute cores changes both speed and size. At the very top, registers are tiny, extremely fast, and private to each thread. Just below that, shared memory and L1 cache are still close to the cores and perfect for reusing data inside a block. L2 cache serves the whole chip as a middle layer. At the base, HBM or global memory is huge but slowest. Efficient kernels minimize slow global accesses and maximize reuse in shared memory and registers. You can think of global memory like a highway. When neighboring threads read neighboring addresses, the hardware bundles those requests into a few wide transactions. That's coalesced access, and it's how you actually reach the advertised bandwidth of a GPU, TPU, or an NPU. If each thread jumps to a random address, the device issues many small, separate transactions. Bandwidth drops, latency dominates, and your expensive accelerator spends its time waiting on memory instead of doing math. Shared memory in CUDA is essentially a user-managed cache. Rather than every thread repeatedly reading from slow HBM, you first load a small tile of global data into fast-on-chip shared memory. That initial load is the expensive step. Once the tile is there, all threads in the block reuse it for many computations, such as multiple matrix multiplications or convolutions. This tiling pattern dramatically cuts global memory traffic and latency, which is why it's a core optimization on H100 and H200 GPUs. Now let's look at CUDA streams, which are queues of work for the GPU. If you don't define any streams, all kernels go into a single default queue and run strictly one after another, A, then B, then C. That's simple, but can waste potential parallelism. By creating multiple streams, you give the GPU several independent queues. Kernels that don't depend on each other can run concurrently, overlapping in time. Frameworks rely on this to overlap compute with data transfers and to keep H100 class GPUs busy. To get good performance from any accelerator, you must keep it busy, not waiting on data. The key idea is overlapping data transfer with compute using asynchronous execution. While the GPU is processing batch N, the next batch is already streaming over PCIe into device memory. By the time compute finishes, fresh data is ready, so there's almost no idle gap. In practice, you accomplish this with pinned memory, multiple CUDA streams or their equivalents, and a carefully designed input pipeline. H100 and H200 achieve their speed not just through raw flops, but through doing many things at once. Streaming multiprocessors handle general compute, tensor cores accelerate dense matrix math, and separate copy engines move data in and out of memory. Because these paths are largely independent, the GPU can overlap data transfers, matrix multiplies, and other operations. When your code and input pipeline are written to exploit this concurrency, you keep the chip busy and dramatically increase end-to-end throughput. When you call something like torch matmul xw in Python, you're really triggering a long chain of optimized components. The Python layer passes your request into a C++ backend that understands which low-level operation is needed. That backend then calls NVIDIA's tuned libraries, such as QBLAS or QDUDNN, which finally launch CUDA kernels on the H100. Your high-level code stays clean, while the heavy lifting happens in deeply optimized CUDA C++ underneath. On NVIDIA GPUs, most of the real deep learning work is handled by three main pieces. A QBLAS powers fast matrix multiplies for linear layers and attention. QDUNN provides highly tuned convolutions, normalization, and pooling. And tensor cores are specialized hardware units that make mixed precision training dramatically faster. From your perspective in PyTorch or TensorFlow, the mental model is simple. Send tensors to the device, run the model, call backward, and step the optimizer. Under the hood, each of those lines explodes into many CUDA kernels. Those kernels are scheduled across grids and blocks in space and across streams in time. Data flows through the memory hierarchy from HBM into caches and shared memory. You don't control every kernel, but with a few key choices you do influence concurrency, parallelism, and how data moves. By the end of this module, the goal is that a GPU profile becomes meaningful. You'll be able to look at a timeline and recognize whether you're compute-bound, memory-bound, or starving the device with input data. With a solid grasp of CUDA primitives, raw traces turn into concrete actions you can take to speed up H100 and H200 training.